Thank you for the introduction. Ricardo was the first user of one of my open source projects, so very happy he's here again today to introduce me. All right, hello everybody. I'm happy to kick off the vLLM track. And honestly, a lot of the things you're going to see today are a accumulation of work that folks have been doing. But today, I would like to stress through overall what has been the vLLM team recent focus, as well as kind of just through the slides talking about what we're doing and what we're planning to do next. So this is structured as a year in review, but also we'd like to give you some highlight of the path forward. So again, I'm Simon. I'm one of the lead of the vLLM project, and currently I'm still a student at UC Berkeley. Right. So vLLM's goal is to build the fastest and easiest to use open source inference and serving engine. Its job is to take large language model, open source, or proprietary large language model and run them on data center hardware. Think of these as running, say, a Llama on NVIDIA GPU, GPT-OSS, on AMD GPUs, and so on and so forth. And very much vLLM is being an open source project where it is contributed, developed, and maintained by the community. And we have more than 1,000 contributors today. We're pretty much reaching the goal of 2,000. But again, number here is only summarizing the amazing work that folks have been doing over the last 2.5 years. And if you really look at the start and adoption and how people are using vLLM today, we have crossed 60,000 stars. And through a very limited telemetry data so we can have knowledge which model to deprecate and which GPU to deprecate, this subset are crossing 400,000 GPU hours running 24/7 with vLLM. And as well as the development side of things, where you have 800 pull requests every month and close to 2,000 contributors. And I would say that the main daily contributors, where people who have waking up thinking about vLLM and go to sleep thinking about vLLM, will probably cross that mark about 50. And where these are large organizations and small startups working all together to make sure vLLM is part of their main strategy and going forward. And today, I'm going to cover state of vLLM in roughly 5 parts and sort of going through the deep stack of what vLLM is about today. And that will cover on the API front, what is new, on the model side, engine side, hardware side, and then finally, I'll touch a little bit on distributed. Note that every single thing I mentioned here, throughout the next today and tomorrow, there's total, including my talk and Nighting talk, about 15 talks touching deep and going deep on each of the topic. So you are welcome to stay here for the entire day today and then go to the Lightning Theater. You'll see a lot more going in depth. So I won't do too much. I will really quickly summarize. So on the API, previously, I would say where the API is going is really focusing on pushing towards the frontier and getting to what I call fully agentic and RO native API. What do I mean by that? If you look at the API as of a year ago, and still the main workhorse and driving force of vLLM API, it is first the LM class, where it is where you leverage it to run large batch job. You use it almost as a drop-in replacement for Hugging Face transformers when it was inferencing one prompt. But here we turn on page attention, turn on continuous batching, and places where you can directly leverage this to score a large list of prompts to be able to generate. As well as what we call OpenAI compatible API server. Here is where you can serve a large language model using the command vLLM serve and be able to run the model on your data center GPUs or GPU clusters. And you can directly point your client code. Instead of pointing it directly to the OpenAI endpoint, you can point it to localhost or whatever host and IP address you have. And this will directly work as is. Now, those has been the main API. But over the last year, vLLM Serve can do a lot more, right? First of all, if your model is natively multimodality, where if you take image, audio, video, right, we can directly serve that as well. I would say it's quite efficient as well. It does re-rank, pooling, and embedding API. So instead of directly returning you tokens or text output, now vLLM can return you a summary of the tokens in the embedding space, a vector in a way. and to be able to power such as Gina or Cohere re-rank API, as well as a lot more pooling and embedding API being used for RAG, as well as for reward modeling. We added responses API, which is a stateful API where you can interleave channel sort and tool use within vLLM, so you can use models such as GPT-OSS, and recently we're working with Minimax, for example, to, again, making sure that this kind of API is where you can leverage the most out of it. We have SageMaker, as well as several other cloud-native API that you directly can drop in and use with your existing cloud platform, as well as recently, you can actually serve OpenAI, open source model, using Anthropic API if you want to directly point cloud code, for example, to any model of your choice. And finally, we have added API for reinforcement learnings, where you can do tokens in, tokens out, to be able to directly get the exact tokens you need instead of getting detokenized or retokenized over time. And we're working on Multimodality API. That is, API allow you to generate potentially not just beyond text output, but also a lot more. And another way of people are using vLLM today is actually breaking it apart. You can actually not just use the API format, rather you directly import the vLLM executor or different kinds of engine class to be able to embed it in your libraries. This is how more than 10 open source large reinforcement learning framework are using vLLM today, where they directly import vLLM and be able to leverage it within their framework. And this is how we make sure we have native support for reinforcement learning as well. All right, that was just API. Let's switch gear a little bit and talk about models. vLLM has always been supporting the frontier of where text model and as well as in general large language model is heading. We support almost all popular text generation models. And the question naturally asks, like, look, vLLM, you support more than 200 architectures today and continue to add in day zero support for new architectures. How do you keep up, and what do you do with all the other ones you don't have enough bandwidth to support? The great news is over the last year, we have added Transformers backend in collaboration with Hugging Face, where you can serve now an even broader set of large language model using vLLMs with just one single flag, /model import transformers. And this is actually a two-way street. That is, on the one side, you can directly run vLLM models that vLLM do not natively support using transformers with the added benefits of new vLLM native kernels, vLLM native distributed pipeline parallelism, tensor parallelism, and MOEs, and a lot more. But also on the transformers front, you can now leverage a lot more kernel within transformers to be able to have both library to evolve and benefit how you are wherever you're using it. And about model support, the way we approach model support is a strict priority stack. Of course, we want to get the model to you on day zero when the model is released, the moment when it's released. But a lot of cases, this means we spend like how many hours we have access to the model, ranging from 2 hours ahead of time access to potentially a month access to focus on accuracy. Because fundamentally what we do is to make sure that the model you are getting is exactly the version that the model provider intends you to use, right? Even on day one, if we can sacrifice a little bit of performance, we'll do that. Because we want to make sure the model you are getting is exactly producing exactly the eval score, as well as over time being able to produce exactly the same log probabilities. So on the right side is a recent feature we just launched called deterministic batch invariant mode, which allow you to be able to replace the same list of prompts regardless of their order, regardless of the sequence, to be able to get exactly bitwise log probability matching. And this, again, smooths the curve of not just us landing new model to you in accurate fashions, but also make sure that you can run this kind of mode in reinforcement learning scenario to make sure that you are not just training the better model, but also the version you're using for rollout is exactly accurate. And then after that, of course, we prioritize performance quite a bit. So on the left is a nightly dashboard that every single commit in vLLM runs through a very expensive performance testing, regression testing to make sure we do not regress. On the other side, there's nothing more than how much we're spending on this as an open source project to say we're spending more than 100K a month to making sure that every single commit is well tested. And we're just getting started and still on our way of getting there. And one thing I would like to highlight is on the model side, it's not just about text in, text out. It's about image, video, and audio in. So vLLM's multimodality support has been one of the state-of-the-art inference engine where what have been highlighted was the Quentin, DeepSeek OCR, and a lot more on exactly we have the right architecture, we have the right modeling support, as well as the right set of kernel to make sure that you can run the latest multimodal model in vLLM. So we launched with Quincy VL, we launched with DeepSeek OCR, which are both names you have heard about. One thing we would like to notice, and potentially one of your takeaway of today, is multimodality trend in 2025. That is, what we're observing is more and more models are natively pre-trained or trained with multimodality understanding in mind. And this actually doesn't, very critically, does not compromise their text model capability. So this is a tweet from Junyang, who is one of the lead of the Quen team, are talking about for Quincy VL, the performance is similar to, especially the text part, is not regressing. And in fact, the state-of-the-art Quincy VL model potentially can be the state-of-the-art text model of its class. And the other side is multimodal output. We're actively working on Hunyuan image as well as many other models that produce better image, audio, and video outputs. So Hunyuan image recently topped the OM Arena chart for text-to-image. They're on top of Nano Banana now, for example, that we're actively working with the team to add support. So on the multimodality front, we very much look forward to enhance, broaden, as well as bring you more and more natively multimodal model that the vision understanding part can potentially even help reasoning and as well as text understanding. All right, on the engine core side, I'll go a little bit faster on the sort of more lower level of the stack. On the engine core, over the last year, it has been a pretty big event for vLLM. That we worked on what we call vLLM V1, which entirely revamped the core engine of what powers runs model on data center GPUs. So we call this a re-architecture. In practice, it is entirely a new folder in the vLLM code that we finished implementing, testing, and migrating everybody over almost without much migration overhead. Now of today, that the code you run is already the new code, and the old code has already been gone and deleted in the code base. So when you read vLLM, you're reading the new code instead of the one from 2 years ago. And the key challenge of the V1 engine, and then the problem we set ourselves to solve, is combining numerous inference optimizations. Over the last 2 years, we have been seeing a lot of different kinds of optimization where if you read the paper or the blog post, they claim significant performance boost, and you read it and take away this is a great idea. But when it comes to adding these into the inference engine, such as prefix caching, spec decoding, chunk prefill, or even on the right structure output, cascade attention, CPU offloading, they actually intersect with each other, right? If you just add them in isolation, you can show them that it works. But how do you combine them together? And furthermore, a lot of this on the left are all touching the one piece of the code that is the core scheduler. The component that decide which request goes into where, and that decide for the next GPU forward pass, what do you put in there? And this is kind of where the difficulty comes in, that we started to draw this kind of matrix where does this feature work with that feature, and how well do they work? Does it actually work out performantly, right? When you turn this on, do you have to turn that off, right? So we're seeing a pretty scary figure where if you use the cross product, the feature matrix of V0, it has been half of it is red. And then with V1, essentially we set out to not just expand the feature set, but also make sure they work together reasonably well as so that when you are running vLLM, all of these are almost turning on by default that you don't get to feel it, right? And then just some highlights that we end up doing. We optimize the engine, a loop, and API server so that the performance is even better. Sometimes folks typically cite the 2x number. When you turn on V1 engine, you get a 2x boost in terms of performance. It's an ever simpler and more flexible scheduler, as well as we added prefix caching capability that is always on by default, right? A lot of this seems to be table stake at this point that will make sure that in vLLM, everything is turning on by default. Clean architecture for parallelism. Yang in the keynote today mentioned all the kind of degrees of parallelism you would do. vLLM support all of that, and furthermore. as well as efficient input preparation, torch compile native integration, as well as, again, as I mentioned, natively multimodality support. And a lot of this combined is the code you are seeing and using today, where vLLM makes sure that under the hood, every single feature have broad compatibility that we think through all the edge cases to be able to serve the latest, greatest model today. And one thing that's work in progress is what we call fully overlapped scheduling, or sometimes also called asynchronous scheduling. This is another exercise in exactly this engineering effort that we want to make sure that when we're adding a new feature for performance, in this case, asynchronous scheduling, that will potentially help you reduce the CPU bubble to about, from some cases, it can be 10 to 20% of the overall execution time if you are, for example, running a small model on the fastest GPU like NVIDIA Blackwell. So how do we get rid of that 20% potential overhead in the worst case scenario? We added asynchrony so that you're preparing the next step while you're executing on the GPU. But the problem is this feature touches everything, right? In order to implement this, you essentially need to resync and think about how do you get this working on all the other features altogether. This has been something where I've been pretty happy to say as of today that it has been on the main branch of vLLM, we're very close to turning it on by default, so that in the next major version of vLLM, you'll be able to immediately see a better performance. I'm going to quickly highlight three more innovations within the vLLM v1 architecture. One is what we call hybrid memory allocator. This has been a paper from the Berkeley team where, as part of SLSP, where non-context models, especially reasoning models today, have hybrid attention. What does that mean? It's not just full attention, sometimes includes sliding window or state space models, where you have complexity in the attention itself. And the problem is how to efficiently manage the memory, KV cache memory, for that has been fairly tricky and hard to get right. And this is where the team have worked on what we call the hybrid memory algorithm, run it fairly well. The other one part of the V1 engine is KV connector. This is where we define the interface to be able to move the KV cache between vLLM instances of vLLM GPU to the CPU region and to disk regions. All of this combined together are growing our ecosystem where working with LM Cache, Mooncake, LMD, we can leverage this connector interface to be able to implement your own KV connector and even sparse attention mechanism. As well as decode context parallel. This is an exact slide from one of the talk from Moonshot, where they make sure that even for the largest model today, you can run it efficiently without scale it out too much and save KV cache. This particular technique is directly from the model provider. Again, signifies the power of open source and open model ecosystem, where they not only build this model, but also, and open sourced it, but also make sure that you can run it well and efficiently with inference techniques such as decode context parallel. All right, let me quickly touch on hardware. There's pretty much two slides I want to mention on hardware. One is, you might have heard of this benchmark from SemiAnalysis called Inference Max. This is an effort that vLLM team has been involved in to make sure that across all the generation of hardware, especially the frontier one, that vLLM can be the core engine behind and making sure that you are getting the best performance out of it. This is not the end state. We're continuously to work with AMD and NVIDIA to make sure that vLLM not only runs well on their current mass market generation that everybody might be getting their hands on, that's H100 and MI300X, but also the latest generation of B200 and MI350, as well as the next generation with Grace Blackwell or the other cluster scale devices. And this is where we continue to work with the hardware team as a collaborative effort to make sure that we're pushing the frontier. And in many cases here, you can see, for example, for GPT-OSS model, that vLLM actually sometimes are better than even the native model that TRT-LM, for example, TRT-LM from NVIDIA. And across all the AMD benchmark numbers, vLLM is being used there as well. And this is one part on what we support so far and how we're advancing the frontier. And the other part is about our hardware ecosystem. So over about 2 weeks ago, we have announced support for vLLM TPU. This is a major effort with Google to make sure that you can run vLLM natively on TPU. In fact, there is a reason that this says a new unified backend, is that because as of a year ago, we have already been experimenting with Google to make sure that finding a way through Torch XLA to get vLLM running well on TPU. But then that has been already powering a lot of inference today for vLLM. And additionally, we have been working on making sure that you can actually get the next best out of performance. And this is why the vLLM TPU effort actually has been an entirely rewrite of that stack as well. So the new stack is vLLM, rich in PyTorch, will have a translation layer to JAX, which has a native state-of-the-art performance on TPU. And again, without the user to do anything, without too much implementation overhead and effort, we have this direct translation layer to make sure that vLLM can run the model exceedingly well on latest generation TPU inference chip, as well as a cluster scale. And TPU is not alone here. There's entirely a full ecosystem of what we call vLLM hardware plugins that both lives within the vLLM ecosystem, like under the vLLM project umbrella, but also outside where in each vendor specific repository. This is where you can pip install vLLM and pip install the plugin to be able to have them to work together, pick up the latest model supporting vLLM, pick up the API server, but pick up the kernel and the hardware-specific driver interaction and other details from the provider themselves. And this list is growing, and we have been seeing a lot more actually just from this public list. And finally, let me quickly say about distributed. Distributed is one of the biggest efforts that vLLM team have gone through this year, and will continue to see it forward. And in particular, one way to think about it is you think about it through what we call the cluster in point of view. And this is where you think about the parallelism, fault tolerance, and elasticity, and think about how would a model being served in a distributed way. Another way of thinking about it is what we call from cluster in. That is, figure out routing, caching, and operation. And we are actually thinking on both fronts, and along with collaboration with with reference architectures. So here on the left is an architecture for LMD. I know it's fairly complicated and hard to see, but the idea here is to stress that, look, we are working with the entire ecosystem. So on the left is LMD, on the right is NVIDIA Dynamo, to make sure that vLLM works out of the box in different kinds of distributed fashion, that you can slice and dice vLLM and sort of shard it in different algorithms. Just to highlight some of these algorithms, one is from LMD, there's intelligent inference scheduling using LM-aware load balancing, where you can route the request in a smart way, as well as PD disaggregation, where you can transfer KV cache in between the pre-fill instance where you process a prompt, as well as decode instance where you generate the responses. And this is where you can leverage a library from NVIDIA called Nexo to be able to transfer the KV cache block, as well as a wide expert parallelism being implemented where you can shuffle the tokens around across hundreds of GPUs to achieve maximum efficiency on the attention side, as well on the expert parallel side. And within it, we also natively bundle a lot of optimization, such as EPLB, which is for expert parallel load balancer, to be able to move tokens around, move experts around, so that you can always have the best distribution of expert for your current workload, as well as very much deep technical effort focusing on dual batch overlap that makes sure that you can always, in the hundreds of GPU scenario, you can overlap communication and computation to be able to achieve maximum efficiency. Yeah. And one thing I forgot to say is that we're here at Ray Summit, and this entire lines of work works extremely well on Ray as well. In fact, today you can use Ray Serve LLM that have all of this bundled up today and directly deploy it. All right, cool. And with that, I'll conclude where we covered in the API side, we are moving towards more agentic and reinforcement learning workflow. On the model side, growing our model ecosystem. On the engine side, revamping the core engine itself to give you the better performance out of the box. On the hardware side, diverse hardware and pushing the frontier. And then finally, distributed, where we focus a lot on best scale-out performance, usability, and being able to out-of-the-box operate it. And with more, you can find us on vLLM.ai and join our Slack, follow our socials. And for now, thank you so much, and hope you are around to see this track. This is only the first talk of vLLM. And for now, thank you so much, and I'm happy to take any questions. And Ricardo will run the mic.
I'll ask the first one while I run across. How do you have time to be the king of vLLM and be in grad school?
Well, that's a good question. So vLLM is this team effort, right? Across Berkeley, across Anyscale, Meta, Red Hat, Hugging Face, and a lot more people here. Actually, probably there's at least 10 people that I can see right now you can directly talk to who work on vLLM day to day. So it's not just me, but also the whole team. Yeah.
Hello, thank you for the great talk. I have a question about the API part. So the OpenAI compatible responses API uses Python dictionary as a response store, if I know correctly. Do you have any plans to support external databases in the future?
That's a great question. And so our responses API indeed only do in-memory, in particular because we haven't figured out the best way, right? We don't know how folks want to use that API. We don't know where do you want to store the states. And this is where we welcome contribution and collaboration on exploring where do you actually want to store all the conversational history around. Yeah.
Questions? Questions?
Thank you for a great talk. I have a question about the model support. Since you mentioned like the battery environments, this is kind of very fancy new features, but this is not like supported very well for the vision language model. So what's your plan like to better support the vision language model?
Yeah. So vision and multimodality has two parts: input and output. So on the input part, we're working on better scale out, so that your input processing doesn't block the inference loop, right? And then so you can have a better ways of getting the input hidden sort of representation and feature in exactly the right place at the right time, as well as multimodality caching. vLLM native support caching for the hidden representation for images and audios, but that's quite expensive. And where do you move them around? Where do you keep them? And where do you put them in? That's yet another front. And then on the output side, this is brand new. So we're still working with everybody who's building Omni model today to figure out the best architecture. How do you orchestrate? What is a model? How many models actually in there to be able to produce an image that follows your instruction is something that's still evolving.
Hi, I had a question about the agentic models. So is there something different like on the inference engine side if you have like a model that has like, let's say, a search engine tool call available to it or something? Is there something different on the vLLM side in terms of optimizations or like, let's say KV cache, for example? Is there anything different there?
Yeah, that's a good question. So if you think about actually just looking at the multi-turn responses, right? If you are just doing chat without any external tool calls, then we can very much treat each response as an individual, right? And then, but for agentic responses, when you're intermixing syncing, co-interpreter, web search, and external MCP tools, the whole request breaking up into small individual pieces. And for example, when you ask a query and the LLM is actually searching on the internet, actually that request needs to be still around because we know that search will come back, but also cannot hold on to that memory for too long because that can take 10 minutes potentially, right? And we want to relinquish the resource usage. But so this is where, with multi-turn conversation within vLLM, we have added and are adding specific optimization to make sure that we're keeping these requests that are in waiting for external responses stage in their KV cache in kind of a special place, so that you can always, when the requests come back, you can immediately start syncing again. Yeah. Cool. I think we have time for one more question.
Sure.
That will be it. Yeah.
Hi, Simon. Great presentation. I had a question related to quantization. And I know that there's experimental support for GGUF. I understand that the architecture behind it is a bit different than vLLM because it has Llama CPP behind it. But what is the state of the support of that kind of quantization? Because with the teams like Unsloth, we get to reduce the size to 70%
Yep.
for models that could eventually run on one GPU or even one node for the biggest models.
Yep. That's a good question. So on the quantization, there's roughly two sides of where we focus our support, right? One is how are people quantizing the model today? And the other part is what are the hardware native quantization formats that will actually give you not just memory savings, but also speed performance boost. So on the GGUF side, it squarely fit into the popularity and how people are compressing the model today. Because that, as you mentioned, it gives you the memory savings, but it doesn't give you the performance boost. And I'm actually quite happy to say we're not experimentally support GGUF anymore. I'm pretty sure it is fully production ready. Quite a lot of models directly use it. Then the question is figuring out what is the best trade-off point where you are compressing the model and preserving the accuracy. So we support a wide, probably more than 10, maybe 15 different algorithms directly natively in vLLM. And then on the other part is figuring out the numerics for hardware acceleration, like FPA, FP4, IN4, to make sure that we're not just getting the memory saving, but also getting the 2x, 4x performance out of the box. Good question. Thank you.
Cool. All right. Let's give another round of applause to Simon.